Good morning, afternoon, evening, whichever it might be. This is about the small little things. We're working our way this year from small to big. Here we have a really neat picture. This is, as it says here, this is a molecule, 5 atoms, and I don't know what molecule it is, but this is the very first vision we ever had of of atoms at the atomic level. You can see, you can barely see the outlines of them. And this is the machine that produced that. This is a microscope. This is not your ordinary run-of-the-mill microscope, obviously. This atomic force scope, and there's its inventors behind. So this is kind of neat. Another visual thing from 2013. I forget who put this together, like 3M, I think, but it's also, if you want to click on it and watch, about made with visions of atoms being put into kind of a little TikTok kind of little cute little whatever. Why can't you believe atoms? Because they make up everything, of course. That may be the first, may not be, but maybe the first of the bad jokes you'll hear this year. But here we go with some basic chemistry, as it says. So this, to me, still, I remember learning this not till I was in college. And some of you know this. This astounding fact, if you click onto this, which we probably will in class, tells you an astonishing thing. That every one of the atoms in your body, except for the hydrogens, was made in the inside of a star that blew up in that thing we call a supernova and traveled through the universe for a good while and ended up all making up you at the moment as you sit there in your desk or at home or wherever you are. This is an astonishing fact that you and I are literally made of stardust. I can't think of anything that would be more astonishing, to be quite honest. So here we have the idea that no matter how abstract it is, like thoughts, for instance, and emotions, everything you and I do and other organisms are due to little particles reacting, chemical reactions. All your nerve impulses, which is where all your thoughts come from, for instance, the chemistry behind those is fairly well explained. So that's called reductionism, reducing all kinds of things down to the chemistry behind them. We continue to learn about specific chemistry that results in specific kind of things like muscle contraction and thoughts and things like that. So some definition things here to keep, because this is fundamentally important to understand. And you've had this before, I know. The difference between a physical and a chemical change is very simple. From time 1 to time 2, a later point in time, do we have different chemicals than what we started with? That's a chemical change. Do we not have different chemicals? Are they just in some different kind of shape or state, like solid, liquid, gas? That's a physical change. So when an ice cube melts, that's a physical change. The ice cube and the melted water are still the same chemical, H2O. If you take a rock and break it, that's not a change of state like the ice cube melting was, but that's still also not a change of chemicals, so that's a physical change. A chemical change, for instance, this will get messy, is when in photosynthesizers they take carbon dioxide and water, those two chemicals, and they turn them into, represented by the arrow, they turn them into molecules like glucose and, glucose and oxygen. I'm getting really messy here, and it's August 1st right now, so my teaching's a little bit rusty. So that's that. So now here we have just another word. Atom is to molecule. Students and people in general constantly mix these words up. In other words, they talk about an atom of water. Well, water's a molecule, so it's not the biggest mistake in the world, but we should call things by their right name. Element is to compound, would fill this in. A compound is composed of 2 or more elements stuck together, just like a molecule is composed of 2 or more atoms stuck together. So now we have a little bit of chemical symbol stuff, and I don't know how much of this stuff you might have had, but this is also something you need to be able to work your way through these chemical symbols. So just like in math, when I'm going to write up here now, Just like in math, when we have the symbol X, which could stand for any number, if we have a coefficient in front of it, that means we have 5 of those things that we call X, right? So this symbol right here, that's a 2 and an O, not a 0. This symbol right here means that we have 2 O's. What does O mean? Oxygen atoms. Now, what's understood in front of this O2 is that there's a 1 in front of this. Just like in math, when you have just an X, you know that there's an understood 1 in front of that. You have just one X there. Here we have just one O2. What does that 2 mean? That thing we call a subscript. Well, that means that here we have 2 oxygen atoms and they are bonded together. I'll make the bond like that. They are stuck together in that kind of package. We have a molecule. We call a molecule. So what does the coefficient 1 refer to? How many packages, how many molecules of whatever symbol follows that we have. In this case, what's called diatomic oxygen, 2 oxygen atoms. So back to this one. Here we have an understood subscript of 1. That this means that these 2 oxygens, once again 2 oxygens symbolized here, but these 2 oxygens are not bonded to each other. They're separate. So that's the difference between these 2 symbols. Both of them mean there are 2 oxygen atoms, but in one case they're stuck together, in the other case they're not. So with that, you should be able to follow now. Here we have 5. 5 what? 5 packages or molecules. What's in each package? 1 carbon, there's a 1 understood, 2 oxygens, and those 3 atoms are stuck to each other. The carbon is stuck to each of those oxygens. Here we have 5 packages. Each package has 1 carbon, but only 1 oxygen. This is called carbon monoxide, right? That's called carbon dioxide. We still have 5 molecules, but now each molecule is a little different than it was over here. Down here now, it's getting a little messy. We have, again, a C and an O, but this time the O is lowercase. And that capital C means we have some kind of atom. What kind of atom? Well, if it was just a C, it would be carbon. And if it was a capital C, capital O, the O would represent a different kind of atom. But lowercase goes with the uppercase, and so this is cobalt's symbol. So it does also make a difference, not only if there are subscripts rather, like the understood 1 here, and coefficients, it also makes a difference whether the letters are capital or small. So this symbolizes 5 cobalt atoms, all separate from each other, not bonded. Okay. So now we break down the atom into those things called subatomic particles, smaller than an atom particle, right? We have 3 basic kinds, protons, neutrons, and electrons. All of you have had this before, so I know this is reviewed to some degree, but none of this is going to be asked of you on the EOC test. We're going to constantly refer to the EOC test because that's a big grade impact at the end of the year, right? But all of this is honors biology topics, and so that's why we're going to study them. But more than that, to truly understand how things work, you have to understand at the atomic level because that's where it all starts. So here we have those kind of particles that are called protons. They're symbolized by that. I just learned that this pen does not write very well on black, so I'm going to try to change it to white. Or maybe I'll change it to yellow. Let's see how that works. Not at all. Ha, how about that? Okay, so here we have a P with a plus. That symbolizes that these have a charge of positive. Positive what? Positive 1. The significance of the number of protons in the nucleus of an atom is that it makes up what's called the atomic number. And we humans have come to refer to that as the identity of that molecule. Or excuse me, see, I just misspoke myself, of that atom. If an atom has 6 protons, for instance, we call it carbon. No matter how many of the other parts it has, electrons and neutrons, 6 makes it carbon, 1 makes it hydrogen. The mass of this proton we have identified very simply as 1. 1 what? Atomic mass unit. We made up these new units for these very small things. So now we have the idea that we can symbolize like this. Sometimes you might see carbon is element 6, oxygen's element 8. Those are two that you probably should get to know, almost like memorization style. Hydrogen 1, helium 2. Helium we're not going to bump into much because it's not part of any kind of biological molecules. So our second part that we find again in the nucleus are neutrons. As their name suggests, they have no charge. They are symbolized, and I can't write it here because for whatever reason I can't write on this. They are symbolized by, there I did kind of, an N with a superscript of 0, symbolizing no charge. They have a mass of 1. Their number can vary in an atom. And since they have a mass of 1, and protons have a mass of 1, and electrons, as we'll get to, have hardly any mass, we refer to the atomic mass of an atom as simply the number of protons plus the number of neutrons. There's the neutron symbol. I didn't have to make it for you. Okay. So now we have the understanding that all kinds of atoms come in different versions of themselves. What's different? Not the number of protons, because that's what defines the atom. So here we have 3 kinds of carbon, 12, 13, and 14. Carbon 12 has 6 protons. All the carbons have 6 protons. That's what makes them carbon. But carbon 12 has 6 neutrons in its nucleus along with those 6 protons, and that's where the number 12 obviously comes from. Carbon 13 has 1 extra neutron. How is it different than carbon 12? It's a little heavier. How is carbon 14 different? It's even a little heavier, right? They're also more rare, and also more importantly, these molecules that we call isotopes that have the same atomic number but different atomic masses, they also have some different properties in terms of what we call stability. A nucleus with 6 protons and 6 neutrons holds together very tightly. We say it's stable. But 6 and 7, and especially 6 and 8, those nuclei tend to, all by themselves, tend to break up in a process we call decay. That's quite different than the kind of decay we talk about, a dead animal on the side of the road decaying, very biological decay. In both cases, it means kind of like breakup, because in that kind of biological decay, they're also breaking up. But in this nuclear decay, it's the nucleus that's breaking up. So we'll come back to that in a little bit when we have a different example. When this breakup happens of a nucleus, it also gives off radioactivity of some particular type, some energy. We can detect that, and we can tell all kinds of things we have learned to from that, and that includes how old that stuff is, and that's what's known as radioactive decay dating or radioisotope dating. We can also use this radiation to kill cancerous cells, and that's radiation therapy in cancer. We can also use it to tell where something is. If we make a molecule with the radioactive isotopes, our little machines that detect radiation can tell where that goes, like in a chemical reaction or a person's body.